Hello guys, so we are today with another new development. Presently what we have seen that the Kalpakkam nuclear reactor has achieved its criticality. Now with this regard, it is very important that this particular subject will not only be helpful in your science, that is your paper 3, but also there will be certain elements that we'll be discussing today that will or that might come in your prelims. So this will also help you to solve certain prelims questions as well, right? Okay, so the development is that for the very first time, what has happened is that India has achieved criticality in its second stage, that is their first breeder reactor, right? We are going to understand about this Kalpakkam FBR. Then we will understand what is the design feature of this particular fast breeder reactor. The design is very important. And then why sodium is used instead of your heavy water or your normal water as a moderator. Then we will see that how this particular reactor breeds more fuel. This particular word, breed, is the soul of this particular reactor. This particular word, breed, right? And finally, we will understand that why this particular reactor is important for India's three-stage nuclear policy, right? India has a three-stage nuclear policy. Initially, we were limited to the first stage. Now we will be moving on to the second stage, or we have moved on to the second stage as we have achieved criticality in this Kalpakkam PFBR, right? Prototype Fast Breeder Reactor. Okay? Okay, so the first development, as we have already discussed, is that it is your prototype First Breeder Reactor at Kalpakkam, Tamil Nadu has achieved criticality. Now what we mean by criticality? We know that this is a fission reaction. Now in fission reaction, what happens is that the neutrons become potential bullets to break other fissile material, right? Achieving criticality means those neutrons which are absorbed or lost, right, is equivalent to the number of neutrons that are formed. Okay? So this is a particular example of criticality. Here criticality is not a negative term. Criticality means that now the reactor has become self-sustaining, that it will continue breaking atoms, breaking your U or plutonium atoms so as to generate energy. Okay? Now, this particular reactor, why it is very important? It is indigenously developed. We have seen that in many reactors, Russians have helped us, right? So you can mention which other reactors where Russians have helped us, right, building such reactors. But this is an indigenously developed and first of its kind nuclear reactor that forms a core of the second stage of India's three-stage nuclear power program. As I have said previously, that it is like till yesterday or a few days back, we were primarily in the first stage, but of the three-stage program. A fast breeder reactor has achieved its criticality. That was the policymaker had envisioned, right? And after so many years, over 70 years, we have achieved this particular feat. And it is designed to generate 500 megawatt electrical power, right? Now, what is important here is the design feature. Now, why the design feature is very important? Because it is the design that helps to breed more fuel. So breeder means what? Breeder means that it breeds more fuel. So this is very ironic. Like for example, if we burn coal, it turns into ashes, right? It gets burned, right? But in breeder means what? In this case, what happens? We burn fuel and we generate more fuel, right? That is the reason why it's called breeder, right? That is, and we'll understand each and every word, why it is prototype, why it is fast, why it is breeder, right? Each and every word. The breeder means that it is generating more fuels. Now, with this regard, like you have to understand that the first word, that is prototype. Why prototype? Because this is it's first, and hence it is prototype, right? It is the first of many to come. So hence it is prototype, right? And it is a pool type fast reactor. Why it is pool type? Because it is entirely submerged in the pool. right? We'll see the image. It is entirely submerged in a pool, right? Now, what is a coolant? You know what is a coolant? Coolant is basically like it absorbs the heat. It absorbs the heat, right? The coolant over here is your liquid sodium. It is your liquid sodium, right? And hence the name sodium cooled, right? Liquid sodium. But you have to ask the fundamental question that why sodium? You have to ask why it is using sodium, right? Why they are using sodium. Now, the reason they are using sodium because sodium has a very high thermal conductivity. Whatever heat it absorbs, it relays those heat. It conducts the heat. So sodium is obviously a metal, right? So and metals are good conductor of heat. And among the metals, sodium has a very high thermal conductivity. So the heat that is generated because of the nuclear fission, and we know that it generates over 2000 degrees Celsius, that the temperature rises up to, right? That particular heat is absorbed by whom? By sodium, and it transfers the heat. It's very good thermal conductivity, and it is very important. If it's not a very good thermal conductivity, then what will happen? That heat will get stored, and then there will be an incident, right? There will be a meltdown, as in case of the terminology that is used in case of nuclear reactors. The best example, one of the best examples where this particular meltdown had happened was Chernobyl. Chernobyl is where it is in Ukraine, right? Now, even though sodium stores less heat per unit mass than water, it flows very easily. As I've said, like it conducts heat very, very easily, right? Now, this is again a very important feature that you have to understand: liquid over wide temperature range. So its melting point. So it is liquid sodium. It is liquid sodium, right? It is liquid sodium, right? And liquid sodium at 98 degrees centigrade, it is liquid at 98 degrees centigrade. Now just see the difference. Boiling point is at 883 degrees centigrade. The boiling point here is at 883 degrees centigrade. Now, what is the significance of it? So basically, when liquid sodium enters the core is where your fuel rods are, right? Where this particular fission reaction is taking place, and it's very, very hot, right? Very hot. So the moment it enters core, the temperature is around 300 degrees centigrade of your liquid sodium, right? Liquid sodium, right? Na, right? Liquid sodium, the temperature is around 300 degrees centigrade. Now, when it exits the core, the temperature is around like 550 degrees centigrade, right? So it absorbs the heat, and it obviously, if it absorbs the heat, the temperature will rise. From 300 degrees centigrade, it rises to 550 degrees centigrade. But there is a gap of how many degrees centigrade over here before evaporation. Boiling point means that it will boil, it starts boiling, right? It will vanish, right? It will liquefy, like it will, convert into gaseous form, right? So from 500, like it has a very high difference. Like what is the boiling point? The boiling point is at 883 degrees centigrade. So a gap of almost 300 degrees centigrade, a gap of almost 3, which is a very safe thing, right? Even if the temperature rises, if the heat rises, still there's a buffer of this 550 degrees centigrade to 883 degrees centigrade, so like around 300 degrees centigrade, there is a buffer. Now there's a reason why sodium is used, because it does not boil easily. Just see, its melting point is 98, like melting point in the sense from solid to this liquid format, it will melt at 98 degrees centigrade, but it will convert into gaseous format what degree temperature? At 883 degree temperature, so that it has a very wide range to absorb heat. Okay? And that's the reason why it's very, very safe. And that's also the reason why it is put inside what? As we have said, it is like a swimming pool, right? It is like a swimming pool, and the entire core is stationed, the core, the pump, everything is stationed inside. So like it is submerged into this liquefied sodium. Remember that. Okay. Let's see the other features. So coolant we have already discussed, liquid sodium. Then fuel. Now this is very important, and this is the basis of our breeder reaction that is happening. The fuel that we have is here MOX or mixed oxide fuel. Now this is very important. Mixed oxide fuel, which is a combination of plutonium dioxide. This is your plutonium, this particular thing is your fissile material, right? Right, so it's 239, right? And then you have your uranium dioxide, which is 238, right? And we'll understand. Just remember now, we'll understand everything. Just remember that it has two nuclear fuel over here. It has plutonium dioxide and uranium dioxide. Remember this, right? Then designed, as I have already said, it is a pool type design. The entire primary heat transport system, including the core where the fuel rods are, primary pumps is that those pumps which pumps in sodium as which is a coolant, right? Because sodium becomes hot, right? It has to cool itself, right? It has to cool itself and then again get transferred to the system. So this is the image. Look, the entire section is submerged. The entire section is submerged in liquid sodium, right? Entire system is submerged in the liquid sodium. The pumps, these are the control rods, sodium. This is your core. This is your core. Here we have what? We have plutonium and uranium. Right? So the entire part is submerged in sodium. That is the reason why it is, again, it is called, so primarily the component here is your pool type design where the entire system is submerged in sodium, right? And the intermediate heat exchanger is contained within a single large main vessel filled with liquid sodium, right? Everything is filled with, is put inside your liquid sodium, right? Now we have understood why sodium transfer heat so well and why sodium is used, because because lots of energy is generated, and sodium is the best here metal to transfer heat, right? Now this is very important that we have discussed that we will understand how the reactor breeds more fuel, right? Now please understand this. This is a bit technical and we have to understand this, right? How it breeds more fuel. So fast neutrons, the reactor uses fast high energy neutrons, right? So there is no moderator. So we have moderator in other old reactors, but here we don't have moderators because we need fast neutrons. Moderators, what does moderator do? It it stops the flow of neutrons, right? But we need fast neutrons, and hence fast. Remember, there was this word fast, breeder, fast, right? Fast because it needs more energy. It needs high energy neutrons. It's needed. And why it is needed? Because this fissile fuel, plutonium-239, it's split because this is a fissile material which release energy, and obviously this release more neutrons. So this is basically your nuclear reactor 101, right? Now uranium-238, it's fertile, it's not fissile. Now remember this very well, right? Uranium-238 is fertile, it is not fissile. Which is fissile? Plutonium-239 is fissile. It breaks, it splits, right? But uranium-238 is fertile, it absorbs a neutron and it gets converted into plutonium-239, which is a fissile fuel. This is a fissile fuel. So that neutron is released, right? This neutron is absorbed by whom? by your uranium 238, which is not fissile, which is fertile. The moment it absorbs neutron, it gets converted into plutonium 239. Now plutonium 239 is a fissile fuel. Now do you understand why it says breeds? Because we have what? We have a fissile and a fertile material, right? Or nuclear element over here. One is fissile, the another is fertile. Now the fissile generates this neutron which bombards your fertile element, that is uranium 238, which is not fissile, and converts you to uranium or U238 into your plutonium 239. Now plutonium 239 is what? Is your fissile. It is not fertile, it is fissile, right? Now what is a breeding ratio? For every 100 fissile atoms consumed, that is every, let's say, plutonium, every 100 plutonium, every 100 plutonium is consumed, 104 what are produced? 104 are produced. So extra 4, hence breed. That extra 4, hence breed, right? Right. Now in this particular case, we'll find that converts a large portion, 70% of U38 into usable fuel. So let's say that you have 10 kgs of U38 that is kept in that MOX. Remember, right? That is kept in that MOX, or that is kept with your plutonium. Plutonium is fissile. U38 is not fissile. It is what? It is fertile. 10 kgs are kept, so that will convert to 7 kgs of what? 7 kgs of fissile plutonium. Fissile plutonium. Right? Okay, I guess you have understood this. Okay? Okay. Now what we will understand is very important. So this is basically your, you see, uranium 238, that is your what? Fertile, not fissile. It is bombarded by neutron. The moment it gets bombarded by neutron, in 23 minutes, it converts to uranium 239, and then after 2 or 3, then it converts into neptunium 239, and then after 2 or 3 days, it converts into plutonium 239. So this is a journey from being a fertile. So this is fertile. To the journey is towards what? Towards fissile. Right? You understand this, right? So from the journey is from here to here, right? So this is your fissile, and it takes 2 to 3 days. Okay. Okay. Now this is very important. Why? Your prototype fast breeder reactor. So like we have understood prototype because it is the beginning of it. Fast, we have understood why fast, because we don't need moderators. We don't have moderators over here, right? Because we need fast neutrons, because that fast neutrons will be converting your uranium 238 into plutonium 239, right? That is the reason why it is fast. And breeder means what? Breeder means that obviously, like it breeds 100, let's say there are 100 plutonium, it will give birth to another more 4, so 104. So that's the reason why there is this increase in your fissile material, right? Now this is the bridge between stage 2 and stage 3, and understand why it is a bridge between stage 2 and stage 3. Look, so we all know that we have a huge reserve. India has a large thorium reserve. We know that, right? Your beach, like beaches of Kerala, Tamil Nadu, right? So we have a good amount of thorium reserves, and one of the highest thorium reserves we have, right? Now, thorium 232 is not fissile. That is the problem. That is the reason why we cannot use thorium. Thorium 232 is a what? Like your uranium 238, it is your fertile. It has to be converted into fissile. It is your fertile, right? It's not fissile, right? So it must be converted into uranium 233. Uranium 233 is again like plutonium 239 is what? This is your fissile. and this is thorium 232 which we have in abundance, बहुत है हमारे पास. This is your what? This is your fertile, right? Now, due to limited uranium and abundant thorium, this conversion is critical for India's long-term strategy, and that's the reason why this is the third stage of our nuclear program, right? Now, if the PFBR facilitates this conversion using its breeder capabilities. Now, understand. What happens is this: the reactor core uses MOX fuel. MOX, you have understood what happens. MOX, we have understood. There were two fuel there. You had your uranium 238 and you had your what? You had your plutonium 239. Plutonium 239 is your fissile. Uranium 238 is your fertile, right? So the reactor core uses MOX fuel while the surrounding blanket can contain fertile like thorium 232. So what it means is that, so here you have your fuel, like the reactor core will have fuel, and then the surrounding of this particular, fuel rods, we will have in this surrounding, very thin, it's like 3 mm, 4 mm thin, will have what? Thorium 232. So this very thin margin, we will have thorium TH232, right? Now what happens is this, then the process of, so this is radial blanket in the sense, this is like a very thin blanket, it covers this particular nuclear core, right? Transmutation means changing happening. 230, remember uranium 238 is converting into plutonium 239, right? So fast neutrons from the core fission convert thorium 232 into fissile 233, as we discussed here, right? Now here we have this, very fast, like we have this fission reaction is happening here. There is no moderator over here. बीच में कोई moderator नहीं है. There is no moderator. So neutrons, what happens is that goes and bombard here in the lining, and converts what? And converts this particular thorium, right? Thorium 232, which is what? Fertile, which India has in abundance. This is fertile, right? Converts this fertile into what? Into what? It converts it into uranium 233, which is again fissile, right? Right. So this process is called transmutation. We are having transmutation in the second case also, but in the second stage, we have 238 uranium 238 instead of uranium 238 and plutonium 239. But in third stage, what we'll have? We will have your let's say plutonium 239. Here we will have plutonium 239, and then they will bombard, which will have uranium. Here you will have what? Here you will have thorium, and this thorium will be converted to what? It will converted to uranium 233. Okay, right? Since uranium 233 does not occur naturally in usable amount, PFBR breeds it for the next stage. It breeds it for the next stage, right? It breeds, it uses for the next stage. Okay. Now, so you have understood, right? So basically the bred uranium 233 will fuel reactors like advanced heavy water reactor, right? So once this bred uranium 233 is what? Fissile. Uranium 233 is fissile, and this uranium 233 is produced where? In the second stage, right? How it is produced in the second stage? Because the neutrons bombard the fertile, remember, thorium 232, converting it it into, it converts into what? Uranium 233, which is your fissile. And fuel for what? Fuel for your stage 3. Fuel for your stage 3, right? So fuel reactors like advanced heavy water reactor is your fuel for the your stage 3, and thorium cycle can increase energy output. This is a significant, like 6 times compared to stage 2, right? That is the energy output of your thorium cycle. Okay, okay guys, thank you.